So hey, yeah. So hey everybody, we're Precision Squirters. We're tasked this year with designing a micropipetter, an automated micropipetter with a certain set of requirements. And this is our presentation of the overview of our design process and manufacturing, all the way to the completion and validation of our design. So during this presentation, we're going to go over the requirements, our design, as I mentioned before, how we manufactured and basically tested this to prove our analysis was correct towards the end.
Yeah, so here's a quick glimpse of some of the critical customer requirements that we were tasked with meeting. Among these is our dispensing range, which was the smallest out of the selections at 10 to 200 microliters with a plus or minus 1 microliter accuracy band. Additionally, we were tasked with remaining within a volume constraint and ensuring our product was cost effective and operational under different conditions. Next slide. Awesome. So our enclosure fits within the volumetric constraints with the longest dimension when assembled at 212 millimeters. The subsystem is composed of 3 components: the motor mount top plate, the bottom plate, and the enclosure itself. These are primarily used to house and mount different critical components such as the ejection mechanism with its solenoid, the limit switches, and the NEMA 17 stepper motor. Being only 3 housing components, the micropipette is easy and quick to assemble and disassemble with a calculated time of approximately 2.5 minutes. An important feature of our design is its open design. In order to allow for a compliance mechanism to flex outwards without constraints, which is going to be explained in the later slides, we added cutouts on the sides of the enclosure that permit uninterrupted motion. Next slide. Awesome. To ensure that our enclosure will be robust and it hold the components housed within it, we characterize our design from a loads perspective, looking at the place most likely to fail, which we found was the top plate under the loads of the motor and the compliance mechanism. We concentrated the loads on the screws that held up the weight of the motor and the linear motion subsystems below it, using the enclosure walls as a support, and looked at the possibility of failure under both 3-point and 4-point bending configurations, both of which saw deflection under the allowable limit. The allowable limit was calculated by dividing the range of linear motion to dispense 200 microliters by the maximum volume to mimic the plus or minus 1 microliter accuracy requirement seen in the customer needs.
For our ejection assembly, we chose a linear solenoid, which provides a reliable, consistent, and robust ejection of the pipette tip. The solenoid supplies 50 newtons of 24 volts of push and retraction force. However, we're only operating at about 7.5 newtons. This gives us an advantage of a compact design and a short switching time between the ejection and the retraction of the arm. Additionally, the arm was 3D printed. Next. So for the iteration, the first iteration of the arm was a simple rectangular geometry, but it was unstable and caused the ejection arm to bend. So for the second iteration, we changed the geometry to a T-shape, and that increased the stability. And we also opted for a semicircle configuration. Our hope in this configuration was to avoid over-constraining the design, but as we found out during testing that it was inconsistent and often did not line up perfectly. So for a third iteration, which was our final iteration, we reduced the arm length and returned to the circle to align it with the nozzle. This guaranteed that our arm would retract and eject. Next. Some of the analysis that we considered to avoid any possible failure in the ejection arm was bending stress, buckling from the supplied force of the solenoid, and continuous loads from the use. From these results, we were able to conclude that the mechanism can withstand the cyclic load over time, and indeed was a robust design. Next.
All right, I will be talking about the design of our piston and cylinder. So first of all, the material that we selected for both the piston and the cylinder was a stainless steel due to the fact that it's resistant to corrosion, its machinability, and high strength. For the O-rings on the piston, we selected O-rings that had the necessary geometry that that we needed to create that seal within the cylinder. So as we move the piston up and down, we can create that pressure differential needed to extract and dispense our liquid. The material we used for the O-rings was a soft nitrile rubber. That is because it was an ideal material for low pressure applications such as this one, and also had very good abrasion resistance properties. And it's also resistant to high temperature conditions, which we need for the bioreactor. Moving forward, we decided to go with a double O-ring design, which I'm sure you guys have seen in the past in fire pistons, but this is because it helps us with alignment and seal redundancy for the piston. As we previously mentioned, our requirement states that we need to achieve liquid dispensing with a very high accuracy and precision. And for this reason, we wanted to have a lot of control of the linear motion of the piston within the cylinder, and therefore have a lot of control of how much volume we're dispensing and extracting fluid, sorry. And for this reason, we wanted to have a very small cross-section design of our cylinder. That way we can yield these very tight tolerances. After all the errors that we can experience in terms of how much liquid we're extracting or dispensing is going to come from the linear motion of the piston through our cylinder. Also, it's important to know that one of our first design constraints that we had with our cylinder was the outer diameter dimension. And this was because we needed to compromise or accommodate our ejection mechanism, which we just talked about, and ensure that the outer diameter of our pipette tip was larger than the outer diameter of our cylinder, so we can ensure we could have that contact surface needed to push out our pipette tip with our ejection arm. Lastly, we did two main analyses to ensure that these two components are not going to be failing, such as the hoop stress of our cylinder and also the buckling of our piston. And after we completed these analyses, we confirmed that these will be safe from failure, at least due to these two failure modes.
So moving on to the linear motion of our system. To achieve it, we have set up the shown here in the rendering. It consists of our NEMA 17 stepper motor attached by an aluminum coupler to an ultra precise M4 by 0.3 millimeter lead screw. And we're using set screws to attach the pieces to make it all put together. At the end of the lead screw is a polymer nut that makes contact with our compliance mechanism, which will be discussed momentarily. When the motor is turned on, the lead screw will bring the nut up or down based on whether or not we need to collect or dispense liquid, which will in turn move the compliance mechanism and the piston and allows for collection and dispension. Due to simplicity in design and modularity, to make it operational, it has a low cost and meets the required budget that was set. And using the stepper motor that we have with the highly precise lead screw is going to help reduce the backlash that would be present otherwise. And thus that would help decrease tolerance stack up so that way large errors don't occur over time with continuous use of the system.
Perfect. Yeah. So basically this system just by itself will have a certain amount of backlash. What that means is your nut is going to be placed against one side of the threads when you're turning the motor in one direction. But when you want to reverse it, there's going to be a gap. That's called the backlash between you're actually thinking you're turning the motor up and you're moving the nut, but you're actually not doing it. So how can we eliminate this backlash and get at the same time like a motion reduction to get even better tolerance? We use what's called a compliant mechanism, which is basically a single component made out of one piece that can bend, and this can perform a multitude of tasks. Specifically for our case, we want to achieve controllable and precise linear motion through what is basically like, you can think of it like a linkage system, like a geometrical system, but instead of having pivots and bearings which have backlash within themselves due to the tolerances between the assembled components, this only has a single joint that bends and acts kind of like a spring, as you can see in the example here that we have. Now, we already knew that this was going to provide a very precise controllable motion for our application, which is great. So it's going to be cheap. It's going to be easy to make because there's so many ways you can make this. We selected, we'll talk about it later on, but to waterjet these out of a sheet of nylon 6/6, which we bought because it has a lot of great properties for our application. So we have low thermal expansion since we're operating in a large band of temperatures from 4 to 70 degrees. It has a lot of great wear resistance and high fatigue life, which is also very important because we need this to last forever. It's also very cheap to make, right? And to buy the materials. So this was kind of like a blank sheet design moment for us because there isn't a lot of information about these compliance mechanisms online. It's kind of like a new thought process. So we had to like get creative. And what we started doing was thinking of like lever reductions to get a certain motion reduction. And you can see our iterative process here where we were prototyping and doing different proofs of concepts, starting with the box that you see on the left, where you have like a motion of the lever, which pushes the one that's underneath it to get a smaller motion on the end. And then we figured out how to make this symmetrical. But the issue with this kind of geometry was that there were limits to how big we could make it within our design constraints. And we were testing out different cross sections to see how those react to different strains as we bend them. So new idea, different geometry. We came up with this. You can see our initial hand drawing on the right. And the idea behind this is that as the nut retracts into up the lead screw, this will push the base against the base of the compliance mechanism against the motor, which acts as a boundary condition, which will push the points outwards. You can see like a little points analysis there where it shows like where they would end up. And basically the piston, which is connected at the very bottom, will be pushed up. So the way we can analyze how much reduction we're expecting to get is by, since this is a symmetrical model, we can use 1/2 of it. The initial part is perfectly square amongst all the sides. So basically your right side triangles, which you're creating there, you're going to have a reduction in one side of the length, which is going to increase one of the other lengths. You're going to have the same hypotenuse, which is your trusses, which those are designed for. And this, we could find that by doing this, we would achieve a reduction of around 1.224, as seen there. But in reality, we're expecting to see a little bit less of this due to like the complex length of the bending members, which are basically springs absorbing deflection energy, storing it as potential energy. So this would all vary. And then we needed to figure out the main aspect of this was how to control the strains that we're getting, right? Because this is all limited by strain. The amount of motion we can have is limited by the strain of the material. So we figured out the allowable strain, and we figured out to the cross sections that we're designing for these members, clamps at both ends, how much can we bend them before they fail? And we figured out that with these cross sections that we use, we need an angle of 55.92 degrees to be within 2/3 of the yield strain, which is what we want to have, 2/3 or lower, because that will guarantee infinite life of the part, since it's never going to be cycled too close to the yield strength of the material all the time. So I have a little bit of slideshows. So this is our initial hand design, which then it went to CAD and assemble, so you can kind of see how it's starting to look. The piston will be connected to the cylinder. And this is our prototype, which we tested successfully as well. So that was also cool. And so, right, as I mentioned before, this is kind of like a complicated design. So we have certain uncertainties, right? Like we have these different pivoting members, but at the same time, we have spring deflections, which will make our design very complicated to do all by hand. So we did use FEA, and we were using the previously learned lessons from the different cross-section members to generate less strains in the member. So you can see on the right, there's a little video I can play for you guys, which shows the deflection and how the strains are now getting reduced at all these different points while we're still achieving reduction in a small space.
So to prevent the system from becoming unstable, we introduced some limit switches being placed into the bottom plate, as seen like in this photo right here, where we have one limit switch in place. And it's to prevent the motor from rotating should it reach certain heights that we find undesirable or just not necessary for the system. So to find the maximum height of that the lead screw can move, the amount of the volume dispensed per revolution was found, followed by the number of revolutions necessary to reach the maximum volume of 200 microliters that was necessary. So knowing that the nozzle diameter that we have is 4.5 millimeters and the pitch of our lead screw is approximately 0.3 millimeters, we found that the volume displaced with one rotation is about 4.771 cubic millimeters, which is also 4.77 microliters per revolution. And for the maximum volume necessary, we find that it takes approximately 41.9 revolutions, which translates to roughly 15,000 degrees to achieve that 200 microliter volume. And converting the revolutions to the maximum height traveled by the lead screw, the system would ideally travel about 12.58 millimeters to reach that volume. And with the compliance mechanism in place, and after we'd done some testing for calibration and for consistent results, there was found to be a reduction of 1.012 to 1. And so we, translating that to the height, we found the maximum height need to be 12.73 millimeters. And we determined to use a 2 millimeter buffer for the limit switches, as placing them at the 0 or the neutral position where the mechanism would be. And at 12.73 millimeters exactly could leave potential for excess liquid that wouldn't be collected or dispensed properly, but still keeping the switches close enough that if the system did go out of control, it could be stopped almost immediately. So having that in mind, the switches would be located at 14.73 millimeters above the 0 and another 2 millimeters below the neutral position. On to the next one.
So our enclosure print was highly iterative, as it was the casing for other components, so its size and features changed considerably to accommodate other subsystems. So we began by mimicking the provided initial design, but then we adjusted it quickly to incorporate the open designs for the compliant mechanism and then the mounting for the solenoid and the ejection mechanism. We also simplified the top plate to 2 mounting holes to reduce the amount of assembly time, and we incorporated slots instead of mounting holes for the solenoid to curb any alignment issues and adjust placement within the enclosure. Our final design was a culmination of all of these changes with the additional mounting rack for limit switches, which was added to the bottom plate for ease of assembly.
The piston and cylinder were machined from aluminum stock due to tool availability in the lab. However, for the final product, we recommend a stainless steel. Next.
Yeah, so for the compliant mechanism, initially, as I was showing in the previous pictures, we were using PETG from the lab, from the 3D printers that we had available. We were doing proof of type kind of concepts, prototypes. The material properties are not the same as nylon. We realized that, especially when you 3D print them, but we didn't care about infinite life before then. So we knew that the final design was going to be made out of Waterjet. So we had to select the right stock out of the right material that would be used to accommodate for all the features that are going to be added to the compliant mechanism that will limit our cross-sectional area. Then we could play with the thicknesses and the accuracy of the Waterjet machine that we were going to use to cut this piece. So we had to use the one that we have available in the lab, and we had some challenges with like workpiece clamping. So one of the features that I added to prevent this issue from happening is to actually add cross-sectional like chassis stiffeners to the device, because when it was cutting and the device wasn't properly clamped and stiffened, any small deflection of the device due to like the intense violence of the Waterjet would cause the wall members to just be cut by the Waterjet. So after properly clamping the piece, figuring out what's the best solution for this, we were getting very precise and machined features. So as you can see here, here's what it looked like after being Waterjet, pretty clean. And then we had to, in a post process, we would have to be removing these stiffening members with just some scissors and a little bit of filing so that it would look like this when it was assembled on the device, with all the holes located on the milling machine and all perfectly aligned, because alignment is critical to this. And here's it assembled within the enclosure and the final product ready to be operated.
So we had to go through also a testing and validation phase, not only to confirm that we were meeting our customer requirements, but also to be able to determine how much we needed to rotate our stepper motor to achieve different desired volumes of liquid.
Oh, you muted yourself accidentally.
All right, here's a video of us going through a testing phase, but essentially what our testing procedure consisted of was rotating our stepper motor at different predetermined angles and then measuring how much volume we were extracting at these measurement, these degrees of rotation, and then we created a plot, which is going to be shown here on the screen, that we got a trend line from, that we could program and input a desired volume and output how much we needed to rotate our stepper motor to achieve that target volume. Next slide.
Yeah, so through calibration of our device, we were able to determine that for every new prototype that we were testing, every new compliant mechanism, we were getting very close and consistent results with the M term of our exponential line. And the only thing that we had to adjust during our testing of different new devices was the bias that we have, which is that you see right there on the equation that's towards the right, it's like a negative 5.7 term. And what this is due to some manufacturing imperfections that we're going to have when we're cutting this piece, because different wall thicknesses will be produced once we have like a proper setup, clamped, stiff, basically machine just running and making a lot of like different parts in a single big sheet. Then we would have more consistent results and we wouldn't have to be calibrating for the bias error every time we have a new device. But at least we know that the linear exponential term is always going to be consistent, because we've been testing at least 5 different mechanisms and they've always been consistent along that range. We just had to adjust the bias error. And we were able to get, during our demo test, we were assigned with acquiring 100 microliters, and we got exactly 100.0 microliters. In the second test, we got 100.1 microliters. So I can say that, yeah, we're definitely within, once it's like properly calibrated, we can hit that plus minus 1 microliter tolerance with this device, because the spring rates that we have from the compliant mechanism will always force your nut to be stuck towards one side of the threads in the lead screw, which will guarantee perfect motion, controllable motion up and down.
And for our budget, we determined that our off-the-shelf parts come to a total of $81.10, which includes the mechanical components such as the limit switches, the solenoid, and the stepper motor. And we also include the fasteners in that as well. And for our custom hardware, we determined that to create one compliance mechanism from the nylon stock that we have is approximately $5. Some of the parts of our design, such as the enclosure and the machine parts like the piston and the nozzle, that they were provided in lab, and thus they were not taken into consideration for this budget. And so in total for all the parts, it brings it to a grand total of $86.10, which is below the customer requirement of $100 as stated.
Yeah, thank you for watching our presentation.
Excuse me, gosh, I unmuted myself and proceeded to burp. So sorry about that. On video too, recorded.
Recorded, yeah.
Yeah.
Forever.
Yeah. Well, I haven't put it up on YouTube yet. As soon as I put it up on YouTube, then I lose control of it. It'll get away from me. Okay, sorry, that was weird. Any questions from our panelists?
Yeah, so this is Rick Miles at Northrop Grumman. I really enjoyed the discussion of the compliant mechanism. Really kind of cool idea. I love the hand-drawn sketches to show kind of the thought process and the evolution of that design. That was really nice. But one of the things that was discussed was you would recommend, if you were going for building things, to build a piece out of stainless steel instead of aluminum, but there was no real reason given. Would like to hear exactly why you would recommend the stainless steel over the aluminum. For
what part? For the
I forget
piston?
which part it was. There was a specific part that.
Oh yeah. I think it was manufacturing the piston and the cylinder.
Yes.
Christian.
Yeah. So the idea was to because of the corrosion from where it's being processed at. So we feel like we use stainless steel, we don't have to worry about that.
Okay.
Yeah. Also, well, since we had our initial constraint of the outer diameter of the cylinder that had to be less than the outer diameter of our pipette tip, right, for the proper contact lip surface for proper ejection, we knew that we had to use the tooling that we had available in the lab to generate the bore of our cylinder. And that had to be pretty, like those walls are going to be pretty thin. So we want to have stainless steel so that we could also have higher strength for those walls so that we don't see failure in case, you know, accidentally for whatever reason, the device just smashes into a wall or something. It's not like bent and out of like tolerance anymore. So we had to think about that. We also had to think that we need to have a taper fit so that the pipette tip will properly seat itself and create a proper seal around that. So with stainless steel and without like any pitting corrosion that you could have in aluminum, especially in a chemical environment like the bioreactor, you're gonna always have that perfect seal. Because I know like it feels like oxidized aluminum can get like kind of like dusty. So I don't think it would create like the proper seal forever. So that's definitely one of the bigger considerations for why stainless steel would be better than aluminum.
Okay. And then could you go to the slide on the calibration results?
Yes. Here.
Yeah, so I really appreciated the discussion because the discussion allowed me to understand that plus or minus 0.1 microliter is a lot better. I don't believe your results off to the left really get that point across. Also think, you know, the first two columns on both tables are repetitive, so there's a better way to show that data than repeating that data over and over again. So just think of a different way maybe to present that next time. But I did, some of the words that you used to describe how you got to the 0.1 microliters of accuracy needs to be on this slide to get across how, because your data there does not show that.
Okay, yeah.
Yeah, that data that we showed there was, we kind of had to go through a series of testing to identify the bias. So obviously our measured volumes is not exactly hitting our expected volume. So this is more of the trial that we went through to find that bias that Tomas mentioned. But I understand why it might be a little bit confusing showing this data and then also talking about how we achieved like an accuracy of plus or minus 0.1. But yeah, we should.
You can think of it as like the learning curve, right? Like we start here, we try different numbers, see, are we being consistent, are we being inconsistent?
No, I understood that, and I thought you did a good job explaining that. Just the slide needs to get across. I'm always thinking someone's going to come across a slideshow later on. They might not have the video explaining the stuff. You need to have the slides explain it as much as possible. That doesn't leave any questions in people's mind.
You're right. Yeah. All right. Thanks. Yeah, that's a good point.
Thank you for that.
I agree. Yeah.
And then one final comment, I also enjoyed the ejection iterations discussion and the development of that. I thought that was very well done. So nice job, guys. And sorry, one more comment on top of that. I hadn't seen any films up until really this presentation, but this is the one type of design where I do believe a film is warranted. So it was a good acknowledgement of things got a little complicated, so now I need to go do a film to see how well my stuff correlates. So good job there. I appreciate that.
Thank you. Yeah. We also made a video. Sean, we sent it to you, but I don't know if you guys like had like the videos that we made, like the 2-minute long videos on the presentation page.
I have not created, I got caught up. I'm currently actually creating the solutions manual for my exam that started 2 minutes ago. I have not created, teaching 3 classes in a semester is not okay. But no, I'm going to create the Canvas assignment for everybody to upload their videos to, so we can create archival, get them all up on the website so you guys can have your demos up on the website for later.
Yeah. All right. Yeah, we have a cool video, so hope you guys eventually see that too.
Okay, great. So I hate to cut off the discussion, but we're actually now a couple minutes over. I started on time and now we're over. So want to wrap it up there so that we can cycle in the next group. But I just want to thank you guys one more time for sharing your design with us and putting together this presentation and coming up with such a cool way to actuate the pipette. So it was very, very refreshing to see that alternative approach that you guys took. So we appreciate it.
Yeah, thank you.
Thank you.
Thank
Thank you very much.
Very good. All right, let me stop